So, today we will see how to make a Dark Souls recreation in Unity, of course. Now, on this first part, we will focus around making our controller, or a basic movement controller, where we have basically two different states. The one state is the normal state where we can move around like this, and the other will be when we have to lock around an enemy, and our camera does a little weird thing. Okay, and lock on to different enemies and change the animations we're playing so that we can move around targeting our own our enemy. Okay, and we create a different state for the camera that basically takes a point between our character and the target and the enemy and acts as it should. And of course we will see how we can evade our enemies both on normal state or on lock on mode state. Now we have a lot of stuff to cover, so this is probably going to be a multi-part series. So let's start with the animator. Now first of all, the camera scripts, you are going to find a link in the description below along with some other cool stuff. And the first thing you will need to do is open up from the script you will find in the description, open up the free camera look and go inside our protect override void update. No, not the script. Go into follow kit, and over here you will see this has more checks, but you want to leave only the if target equals null, or this one. Yeah, I think this was it. So if target is not equals null, and leave only this. It had some check to see if you have a rigid body, and that rigid body wasn't kinematic. Only then follow call this the follow function. Now with out of the way, let's go back and see our setup. For our player, we have our basic setup. Okay, animator, rigid body, capsule collider, and here you will see the player and our world without any of the image effects. Okay, and we have also have a reflection probe over here, just because we have a lot of metals over here, so why not? Now of course this bakes real time, so it's a little bit more it's a little bit more performance needed. So anyway, so our basic setup: animator, rigid body, capsule collider. Okay, check all the values over here you have to check, and we will add two new scripts, which is one is player control and the other is player animation. I have the player animation disabled because I am enabling it from our player control to make sure we have initialized this script has first initialized it, because we are taking stuff we are taking references from the player control script. Next, we need to create of course the animator, and of course for the animator you will have to have animations. Okay, I'm using the Miliax pack, which is free on the asset store, so, or at least it's free for now, so you can use that or use whatever else you like. Now this is the basic this is the animator, but we're going to work mainly with three states over here. We have our locomotion on normal mode and we have our locomotion on lock on mode. Now of course I could probably combine these two together, but this way we have some stuff more clear. And then the third state we're going to use is of course this rolling animation. So our locomotion normal, one directional blend tree, and you will see over here, let's drop our knight over here so that looks better. If you see, when I hit play, of course idle when forward is at 0 is at the idle, when it's 0.5 starts walking, when it's at 1 starts running, and at 2 he starts run even faster, and of course his sword gets inside his head, so that's probably going to hurt a little bit. So this is our default state, and then we have our locomotion lock-on, which is a 2D freeform Cartesian, and it takes two parameters, which is the sideways and the forward. Okay, the basic values as we have done a lot of times before. Okay, forward, backwards, and of course this has the same problem as the diagonal, so you can add one more state from there. So the next thing we need to do is we have our stand roll animation, which is basically a rolling animation, which is the roll, and of course this animation has some problems on the legs, but it's pretty good to as a placeholder. Okay, so to transition from both states, either it's the normal or the lock-on, we need to have a trigger, which is a trigger of roll. Okay, and then from both states we do not want exit time, and then from standing to roll we return back to locomotion normal based on exit time. Now it didn't matter which one of the two I will have to go. Okay, since if it wasn't for lock on, yeah, they transition back to each other pretty much as the same, since they have the pretty much some animations are shared alike, so it's no problem at all. Okay, and to move from locomotion normal to locomotion lock on, we have boolean. Okay, lock on, if it's true we'll go to lock on, if it's not we go back. Okay, now one thing we need to make sure, because when in Dark Souls in general, when you're pretty much doing something, you cannot move. Okay, so when you attack you cannot move, or when you roll you cannot attack and stuff like this. Now you won't be able to attack since you'll be since there's no connection to attack states. Okay, and we'll probably see the attacks on the next part. Okay, it's just because we have a lot of stuff to cover. So we also have a boolean can move, and we reset it so that we can actually move based on the transitions from this animation. Okay, so we have some behavior over here, some state behaviors. We will see in a little bit what we're doing. So without this is pretty much, you will need these three animations to work on this video, and we will see all the other stuff you'll see around over here on the next part. So let's go to a player, let's go to a scripts. Okay, create player control script. Now if you're following along, if you have followed along previous videos of this from the channel, you will see that this is pretty much a copy-paste work from everything else we have already done. Now we have our references we're going to use. Okay, rigid body, animation, capsule radar, we're not using it, so anyway. A transfer for the camera, a public transfer from camera holder, but I do not want to have it in the inspector, so I'm using hide in inspector, but I'm going to access it from our player animation script. Okay, so we're not getting them writing the same stuff all over again. We have how fast we move when we are locking speed, how fast we move when we are at normal speed, and the actual speed we were changing. Then how fast we turn, a direction we want to look at, a place to store that direction. Okay, we have all our inputs, which is basically horizontal, vertical, and the roll input, and I want them to be public just because, as I said, I want to access them from player animation, so I'm not getting from everywhere the same I'm not getting from everywhere references, but I want to get them just from here. Okay, if we have lock target, current target, if we want to change target, we use all this on rotation. If we can move, at least with all our enemies we have pretty close to us. We will see how to update dynamically this list on later videos. Okay, this is a target for our own camera, because we do not want our camera to always be facing our own player. Okay, and target speed, how fast the camera will change positions, and our target position for the camera. Start. Get all our emphasis, set up animator. Once again, it's this. Okay, we have done it a lot of times before. So, get component player animations dot enable, so that we enable this component. Okay. Next, we have a fixed update where we are going to call all our functions. Right. So we need to take our inputs, of course. We need to update values from our input, and we need to handle the camera target, since it's not pretty much. It doesn't pretty much matter if the player can move or not. The camera has to update its position every time. So if we can move and we do not have target locked, we change the speed to normal speed, and then we have the movement normal. But if we have a lock speed, we change the speed. If we have a lock target, we change the speed to lock speed, and we check if we have enemies. So there is at least one enemy into our list. We handle movement on lock on, and we handle the rotation on lock again. We call these functions. Okay, if we do not have enemies, then we cannot lock any target, so we close the lock target and returns the loop and plays this logic instead. So this is for fixed update. Let's see, or better yet, let's see it one by one. Handle input. Horizontal, vertical, roll input, get button. Now fire 3 by default is left shift. Okay, so if we want to store, we need to store the direction, and that is the camera holder dot right. So we need to change to save the direction of the hold right. Now you can probably say store the direction of dot forward, but since I have that the same way in previous videos, I just want to copy paste it. But since it works as it should, then there's no problem. Then we're calling the change target logic, since you can say it's based on handle input. Okay, this is pretty simple. If we press the fire 2, which is the right click by default, we change the lock target to whatever the lock target is not. So if the by default it's false, it will return true. Now we need a way to cycle through our enemies. Okay, so I just added a keycode.q. So when we are pressing Q, we check if our current target is lower than our enemies.count -1. So if we have only one enemy, enemies.count will be 1, but our current target will be 0. So 0 is lower than 1, of course. Then it will try to add to our current target. Then it will return an error, an array exception error, of course. So we check if it's lower than our list -1, and then only then we add to it. Otherwise, our current target will be 0. So it will be the first target, the first enemy we have on our list. So that's handle input, that's change target logic, and then next we'll go to handle movement normal. Now this is pretty much most of the stuff you see here, they were on the Max Payne video. So let's see it a little bit. Can move. We check if the animator can move. If the animator bool is at can move, then we can move. Okay. We find the direction. We find the direction forward and the direction of the sideways. Okay. Direction forward will be the stored direction multiplied by horizontal, and direction from the side will be camera holder dot forward multiplied by vertical, and this is and I've wrote this backwards, and I've did the same on the Max Payne video. So anyway, okay, so that's why we had cam holder dot right and dot forward, and we have the sides the cam holder dot forward. Anyway, so we find the directions and we multiply it by our input. Okay, so if there's no input, all this will turn 0, so there's not going to be any changes. So if we can move, then we add force to a rigid body. Okay, and that force is direction, either direction forward plus direction on the side, and we normalize it so that we do not move faster when we hold both axes. So if we are moving directionally, it will always, the maximum that is going to be will always be 1. Okay, so we multiply that by the speed, subdivide by time dot delta time. Okay, next we need to find the direction position where we are going to rotate to. That direction position will be our transform position plus our the stored direction we have multiplied by horizontal plus our camera forward multiplied by vertical. We need to find the direction, which is that position minus our transform dot position. Okay, we level the y. We need to find the angle, and we find it using, we need to find the angle between our transform dot forward and our direction. Okay, there's no jumping in this video, so let's delete that. So before we do something with our angle, where we use it over here, we need to use the animation. We find the animation value which are going to use, which is both the absolute value of our horizontal axis and the absolute value of our vertical axis. And since if we are moving diagonally, this can be 2, and we do not have 2 on our blend tree, we clamp it between 0 and 1, so we pass the animated value. Now you can add here if you're pressing a button to change that animation value to 2 so that it will run. Okay, pretty much what we did in the third person shooter series actually. So this is nonsense. So we pass it on the animator on the forward. Okay, we pass the animation value. Since it's one directional blend tree, doesn't matter which axis we pass, we will always pass it on the forward. And then since we do changes on the animator over here, we can say that the lock on should be false, so make it false on the animator. Okay, then if we are not pressing anything, if we are pressing an axis, so both horizontal and vertical are not 0, and then we check if our angle is not 0 and we can actually move, then we rotate a rigid body using quaternion dot spherical interpolation from our transform dot rotation to quaternion dot look rotation towards the direction we find over here. Okay, by 10 speed multiplied by time dot delta time. Okay, and this is how you move when you are not locking on an enemy. Now we did this. Let's see this handle movement when we have lock on an enemy. Now this is pretty much the same stuff we did on the Assassin's Creed video. As I said, a lot of copy paste is going on here. So we take our camera holder, which is camera.parent.parent, and I should have stored that somewhere else, but anyway, we have our camera forward, camera right. We scale the vector, we bring it to the correct scale, and camera right, we pretty much do the same thing. Now You can do the same stuff as we did over here, but yeah, this is another way, another approach to that. So decide which one you want to make. Now we need to find the move vector based on our camera's direction. Okay, pretty simple. So that will be vertical multiplied by camera forward plus horizontal multiplied by our camera dot right, and it's exactly the same as this stuff over here. Then we find the forces that are going to be applied to the rigid body. Okay, move forward, move sideways, the same stuff as before, and then we apply those forces to our rigid body. Okay, it's not something you haven't seen before. And then we pass the move vector and we pass it to make it values that the animator can use. Now we take the move input from wall position and we want to turn it into local position so that we play the correct animations basically. Okay, and play the correct animations depending on where we are looking. So local move, vector 3 local move. Okay, transform dot inverse transform direction move input. We pass the direction and we turn it from wall position to local position. Now the turn amount will be the x on our local position, and the forward amount will be the z of our local position. And that thing is, the forward will be the z. So if it's straight ahead of our target, then we're moving forward. If we're moving away from our target, we're passing -1 to our animator over here, and in turn to our blend tree. Okay, and for sideways pretty much goes the same way. Okay, so if turn amount is not equal 0, then we multiply it by 2 so that it goes faster. Okay, you can if you have more animations, you can add them so that it will make a little bit more of it will make the blending a little bit better, but this way you can make sure that it actually plays the animation instead of moving. Comment this out and see what it does. Pretty much easy stuff. So since we're changing values for the animator, let's change all of them over here. We are on lock mode, change the boolean of lock on in the animator. Pass the forward amount, we just said what it is. Pass the sideways, we just said what it is. And that's pretty much how you move when you have a lock on. But since we are locking on a target, we need to make sure that we are also looking towards the target. And to do that, we need to handle the rotation on lock. So we call this function handle rotation on lock. Okay, we have our look position, which is basically our current enemy. Okay, our look direction will be the look position minus our position. We kill the y, and then we rotate to that target. We create quaternion rotation, quaternion dot look rotation look dir, and then transform dot rotation or rigid body dot rotation. And I think we should probably use rigid body dot rotation over here, equals quaternion dot spherical interpolation from our own rotation to our target rotation, all that by time dot delta time multiplied by turn speed. Okay, so handle camera target. So without now, because we want to have our camera to do when I'm looking on an enemy, we want to make the camera look towards that enemy. Okay, but it's not actually looking towards our enemy because we always want to make sure our player is inside our view sphere where our camera is looking. Okay, so we're not losing our enemy. You will see the camera is actually not targeting the player, but it's targeting this camera target, another game object. And let me enable its mesh renderer so that we can always see where it is. Okay, and you will see that it's based on an offset a little bit forward of our player, and it's always looking towards our enemy. Okay, so our pivot of our camera or our camera holder is actually based on this position. When I'm not on lock mode, you will see that it will return towards our player, and when I still lock on and when I change target, you will see that it changes. Now, of course, to avoid something like this where we're not seeing at all our character, you can change the offset of inside the camera. Okay, you can change the Z based on a lot of stuff. You can do a lot of stuff with this. Okay, now the logic behind this, where we move our camera target, of course this is an empty game object, just you only need an empty, but I also have a mesh renderer so that I can debug it and see where exactly it falls. So let's go back this. The logic that we handle all that is inside our handle camera target. So if we are not locking on a target, the target position for our camera target will be our own transform.position. But if we are locking on a target, then and we have enemies inside our list, of course, then we need to find the direction towards our enemy. We take our current target, and to find the direction, we subtract our own transform.position from its vector. We kill the y as always, and we need to find the distance between our own player and our target. Okay, vector 3 dot distance transform.position and our current target. Target position, the target position where we actually are going to be, will be the direction normalized. Okay, because otherwise if he was too far away, then we'll get some pretty wild results. Okay, and we multiply it by distance. If we subdivide now by 2, you will see that our little cube over here, when I'm locking in, you will see that this cube will always be at the center between our player and our target. So if we subdivide by 4, then that position will be at 1/4 of that distance of our player and our target. Now, of course, you can do whatever you want. You can add this to 5, to 6, or whatever percentage you want it to be. Okay. Now, by itself, though, this will have a position that it's not based. It will be based on wall position, and it will not take into account our own transform.position. So it will not it won't be at the correct position. So the only thing left that we need to do is actually add to our target position. It's actually add our own transform.position. Okay, and just to make sure that our player is not too far away, if the distance is higher than 20, then it will not be locking the target anymore. So let's make it something smaller, because 20 is actually pretty far away. So let's hit play, let's aim, let's also add, and if we go back, you will see that after 10 points, then I can stop looking at target. Okay, and you can change the target. Now, of course, how you decide the target is pretty much linear. Okay, so we can change that on a later part to make a check to see which one is closer and stuff like that, and change it that way instead of linear. Okay, so the only thing left for this part will be the actual roles over here. So this is where player animations come to play. We need a reference to a player control. We need a public float, a roll speed, how fast we are going to roll. Now keep in mind I'm changing these values from the inspector, so these are not the ones I'm actually using. Okay, we need both the references over here for our input, which is horizontal vertical roll input. Okay, but we're not updating them and we're not checking them from here. We just take the references from our player control. A public bool if we are rolling, a boolean if we have rolled, direction position, store direction, camera holder, rigid body, animation, if we have a direction forward, the direction sideways, and the direction we want to rotate to. On start, player control, get component player control. From our player control we take the camera holder. Okay, we take the references to a rigid body and animator, or if you make them public inside player control you can get them from player control. Okay, fixed update. This roll input, this horizontal, this vertical, we take all the references from player control. So whatever we have on player control we will also have in this script. Start direction, camera holder dot right as it was on the previous script. If roll input, if we are not rolling, so even if we are if we press the fire 3, the roll input, when we are actually rolling, it's not going to happen anything. Okay, so if we are not rolling, we'd say that you cannot move into our player control, so we are not changing directions mid-roll. Okay, and we say rolling is true. If rolling stones, if we do not have a direction, we need to find the direction we want to roll to. Okay, direction forward, direction sideways, the same way as before, but we only do it in one frame. Take the sort direction multiplied by horizontal, we take a camera holder forward multiplied by vertical, and it's still the other way around. Okay, so this is direction forward, this is direction sideways, since it's just a copy paste job. Direction position equals transform dot position plus store direction multiplied by horizontal plus camera holder dot forward multiplied by vertical. Direction, we find the direction, which is our direction position minus transform dot position. We kill the y as always. Okay, we say to the animator trigger the roll animation, and we have a direction. So the next frame it will not keep updating, it will not update the direction we are moving. We want to add force toward the direction we just saved. Okay, and we do it this way. We take the R forward and we take a sideways direction, which is the other way around, as I said. We normalize it, and all that we multiply it by roll speed by time dot delta time. We need to find the angle and animation value. We don't even need this. Okay, we need to find the angle, and if the angle is not 0, then we say to a rigid body rotation, we change the rigid body rotation based on spherical lerp from our transform dot rotation towards look rotation towards the direction we just found previously. Okay, and all that 15 by time dot delta time. Now of course you can make this public. Now we need to check for the angle, because we're getting errors if we're getting a warning, not an error, if we try to look on a rotation that is exactly the same, so you avoid a warning over there or even an error depending on something. So this is how you find the angle, and then the only thing left to do is actually all this will make the animator play play this animation, but as you notice in the script we're never actually disabling all our booleans. So the rolling is never disabled inside the script, and the hash direction is also never disabling in this script. So just like this, the only thing we're going to happen is that we're always going to be adding force towards direction. Now, the way why I'm not changing, I'm not disabling these booleans from inside the script is to avoid having to change different timers based on different animations. So we can create some animator behaviors over here, and animator behaviors, we have used them before, pretty sure you know what it is. Okay, to create an animator behavior, you need to take from, instead of mono behavior, you need to take from state machine behavior, and you have available these functions. So what we want to use is on state exit, which is when the state of the animation has left the state, when mechanism pretty much left the state and went over here, it will run this logic. And in our case, the logic we want to run is on, not enable movement, on close rolling. Okay, so when we're leaving the rolling state of the animator, we have our player animation, we take the component, we find it from the animator, but I think even if you write transform.getComponent, it will still give it, or not, so whatever. So we take our player animation, we find it from animator.getComponent player animation. This by default will take it will go to the transform and try to find a player animation component. Okay, and then we take our rolling, we turn it to false, and our hash direction to false. So after we left our rolling animation, we can actually roll again. Okay, so for how long the animation state is going to be, it will depend on how much force we are adding on our roll. Okay, and the only thing left then is to actually enable the movement, and I'm using a different animator state behavior because we are going to enable to use this script over here, this animator state behavior, on a lot of other states. So we have animator the same way as we did it before on the other animator state behavior, where we say we get animator get component player control can move equals true. So we can move without this. Let me comment this out and you will see what will happen. Now don't forget to actually drop them over here. You cannot drag and drop. You need to click add behavior and it will automatically find you the animator state behavior, the scripts that derive from state machine behavior. Now without enabling the move, the can move boolean, you will see that if I roll, now I cannot move and I'm pretty much stuck. So we need to enable that, or enable, instead of directly going to player control, you can enable this can move boolean. And I think I should have done it that way, but anyway. So that's pretty much it about this part. Now let's see, I've added some image effects to make it look a bit more Dark Souls-esque, you know. Okay, they are pretty much it's not in any particular order, they're pretty much random how I've added. I've just add stuff and see if I like it, and if I don't, I change them. Okay, and I think we're pretty much done for this part. And so on next part we will see how to actually attack our enemies. Okay, and we will see how to add even more stuff, and we will create an animations, because of course we need to have animations, and we're going to create a health bar, and of course to make, now I don't know if I'm going to make a health bar actually, but we were going to enable our character to be able to die at least, because what is Dark Souls if you cannot die? Okay, so if you like this video, don't forget to like the video, subscribe for the next part and some more awesome stuff. Okay, if you like this video and want to see more, you can support me on patreon.com, because you know this stuff takes a lot of time to prepare, to record, and to make, and of course to research on stuff on how to make new mechanics, and any help is always appreciated. And there are some gifts which I'm pretty sure you know what those gifts for backers are. So I'll see you next time.